Le Chatelier's principle is used to predict how changes will affect the position of equilibrium. The position of equilibrium is an important consideration, especially in industrial chemistry, because it relates directly to the yield of the product. So the further to the right the position of equilibrium, the higher yield of product we've got. And so that's quite important in industry. Now there's several ways in which the position of equilibrium can be altered. Some changes will push the position of equilibrium to the right, while others will shift the equilibrium position to the left. So if we are wanting to increase the yield of the product, we're trying to push the equilibrium position to the right. The equilibrium position can be changed by altering the concentration of either the reactant or the product, the pressure if the reaction involves gaseous reactants or products, or by altering the temperature. Le Chatelier's principle states if an external change is made to the reaction conditions of a system at equilibrium so that it is no longer at equilibrium, a net reaction will occur in the direction that counteracts the change. The internal change will oppose the external change. So basically what that means is that whatever is done to the reaction conditions, the system or the reaction will change in such a way that does the opposite. So if you increase something, it wants to decrease it. So it will shift in a way that achieves that. So we'll have a look more specifically at some of these changes. Okay, so we'll start by looking at the effects of changes in concentration. And when we're changing the concentration, we can either change the concentration of a reactant or of a product. So if we're changing the concentration of a reactant, we've got two options. We can either increase the concentration or we can decrease the concentration. The same goes for the concentration of products. So we can increase the concentration of products. So this might involve actually adding in some more of that product, or we can decrease the concentration of the product, and that might be done by removing the product as it forms. So as we have a look at this, we're just going to consider the reaction shown here, which is basically the conversion between these two different oxides of nitrogen. So firstly, we'll have a look at what happens if we increase the concentration of the reactant. To counteract this increase in concentration of the reactant, the system will want to decrease the concentration of that reactant. Now, the way it will decrease the concentration of that reactant is by using it up and converting more into product. So what that means is the reaction is going to be pushed towards the right because it's going to be consuming more of this to decrease the concentration, which means it's going to go to the right and we're going to see an increase in concentration of our product. So it will increase the yield. So if we decrease the concentration of our reactant, the system will counteract that by increasing its concentration. So we'll see a rise in concentration of this. And the way it will do that is by converting more of the product back into the reactant. So by decreasing the concentration of a reactant, the system will want to increase it. So that will favour the reverse reaction and give us a lower yield. So if we increase the concentration of a product, the system will respond by wanting to decrease that concentration. So in order to decrease the concentration of the product, it will be converted back into the reactant. So that's going to favour the reverse reaction. So it will push equilibrium to the left. Now, if we were to decrease the concentration of a product, the system would respond by increasing the concentration of that product. So that means that more reactants would be converted into products to increase the concentration. So we would see a greater yield as equilibrium is pushed to the right. Now, a way that might be achieved is to remove the product as it forms. So if you remove some of the product from the system as it forms, that's essentially decreasing the concentration. So if we have a look at all of these possibilities, and we're considering wanting to increase our yield of products, we can see two situations in which that occurs. So we can either push the reaction equilibrium further to the right, or increase the yield of the products by increasing the concentration of the reactant, or by decreasing the concentration of the product. Now, you're already familiar with looking at concentration versus time graphs. So we can see here that we've got our reactant, and over time the concentration is decreasing until equilibrium is established. And with our product, the concentration is increasing until equilibrium is established. Now, it's at this point down here that a change has occurred. So in this situation, we're looking at extra reactant being added. So we have increased the concentration of the reactant. So what you're going to need to be able to do is recognise what sort of change has occurred by using these concentration versus time graphs. So in this specific case, we're looking at what you can observe if we increase the concentration of a reactant. But you may also need to use this to look at a decrease in concentration of the reactant, or an increase or decrease in the concentration of a product. So in this one, we're looking at an increased concentration of a reactant. The way we recognise that on the graph is this vertical line. So what it means is, in an instant of time, not over a great period of time, there's been a sudden jump, in this case up, in the concentration of a reactant. If we had been to remove or decrease the concentration of the reactant, that would be a vertical line straight down. So what we've noticed, we can see that that's a change. By looking here, we've increased the concentration of this substance, which we know is our reactant. Now, after that change, the system is going to be trying to re-establish equilibrium. So both the forward and reverse reactions will be occurring again until equilibrium is established. So we can see the concentration of our reactant decreases until equilibrium is established, and again the concentration of our product increases until equilibrium is re-established. And we can see we've got a new equilibrium position established because the concentration of these two substances are at different points than what they were initially. And I just want to point out again at this stage that the vertical line is going to indicate the change in concentration, at being the external change made to the system. So if it's a vertical line going up, it's going to be an increase in concentration. If it's a vertical line going down, it's going to be a decrease in concentration. Okay, now we're going to have a look at how changes in pressure can affect the equilibrium position, keeping in mind that when we're considering pressure, it needs to be a reaction that involves gaseous reactants or products. So we've got two options. We can either increase the pressure or we can decrease the pressure. And we'll consider the same reaction when looking at this. taking note that we've got gaseous reactants and products here. Now, the way the system will counteract a change in pressure is by pushing the reaction in a direction which creates more or less molecules. So the greater number of molecules we have in a particular area, the greater the pressure is going to be. So if we change the pressure, it's going to counteract by altering how many molecules we have. And it does that in accordance with the mole ratio. So if we have a look at the ratio of reactants and products here, on the left hand side we've got 1 mole of reactants, and on the right hand side we've got 2 moles of products. So the right hand side is going to have more individual molecules than the left hand side. So if we are to increase the pressure, the system's going to re-establish equilibrium by decreasing the pressure, and it will do that by favouring the side with fewest molecules. So in this situation we can see we've got 1 mole on the left as opposed to 2 moles on the right, so it will favour the left hand side. Now if we were to decrease the pressure of the reaction equilibrium, the system will want to increase the pressure, and it will do that by shifting towards the side with more molecules. So the ratio is 1:2 in this case, so we can see the right hand side has the more molecules. So the reaction will be pushed to the right in this situation. So we have a look at the concentration versus time graph again, and we'll have a look at what a increase in pressure looks like. So we can see here, again, we've got a vertical line. Increasing the pressure is essentially the same as increasing the concentration, because one way that is done is by decreasing the volume. So increasing the pressure, we have a greater number of particles in a smaller volume, which is the same as increasing the concentration. What you'll notice as being different from the increasing concentration of a reactant or product graph that we looked at above is that increase in concentration is the same for both the reactant and the product, so they're affected equally. So a change in pressure will make a change in the concentration of both the reactants and the products. Now if we have a quick look at the reaction pathway, we had our initial reaction occurring here, so our reactants were decreasing and equilibrium was established, and our products were increasing until equilibrium was established. We've increased the pressure, which the system is going to want to counteract by decreasing the pressure, and we determined that meant it was going to favour the reverse reaction. So we're going to have the left hand favoured because it had fewer molecules. So what we see to establish this new equilibrium, we now see an increase in concentration of our reactants, which means that the reverse reaction is being favoured, and a decrease in concentration of the products. So just take note of the different shape of the graph there. So we can see we've got this sort of shape when the forward reaction is being favoured, as opposed to this sort of shape when the reverse reaction is being favoured. Lastly, we're going to have a quick look at changes in temperature. So either an increase in temperature or a decrease in temperature. So this relates to whether a particular reaction is endothermic or exothermic. So an exothermic reaction releases energy, so we see a temperature increase, and an endothermic reaction absorbs energy, so we see a decrease in temperature. Now, when we look at the thermochemical equation, we have got our thermochemical information here. Remembering that if this is a negative value, it's an exothermic reaction. If it is a positive value, it is an endothermic reaction. Now, this figure over here relates to the forward reaction, okay? So that means the reaction occurring in this direction, in this case, is endothermic. If the forward direction is endothermic, that means the reverse reaction is exothermic. So if we are to increase the temperature, the system will want to decrease the temperature. And it will do that by favouring the reaction which is endothermic, because that's going to absorb some of the heat. So in this case, the endothermic reaction is the forward one. So an increase in temperature will favour the forward reaction because it is endothermic. Now, if we decrease the temperature, the system will want to increase the temperature. And it will do that by favouring the exothermic reaction because that's going to release heat. So in this case, that's the reverse reaction. So we would see a decrease in the yield. So if we have a look quickly at what a temperature change looks like on our concentration versus time graph. So again, we've got our reactants decreasing until equilibrium, products increasing until equilibrium. And we can see this is where our change occurs. Notice we don't have any vertical line in this case. So by looking at the graph, we know straight away that the change has not been a change to concentration or pressure because there is no jump or drop in the concentrations. So at that point, we just need to then consider the shapes here. So we looked at the shape when we looked at the last graph. We can see this shape indicates that the forward reaction is still being favoured. So we know that the forward reaction in this case is endothermic, which is consistent with an increase in temperature favouring the endothermic reaction. If the change in temperature favoured the reverse reaction, we would see the other shaped graph that we looked at above.